Scroll up. Scroll more.
Should be. If you go up and
Where?
maybe if you, there should be a way to hide the stuff on the right.
Maybe if you figure it out later. Too much description, right?
Yeah, if you like open it completely, all the way on the right, there should be a button that says hide. Yeah.
This one?
Yeah. There you go.
Right. Do you guys understand the difference between this notation and this notation?
Yeah.
Do you understand this one? Tell me
Yes.
what it is.
I believe that A is a subset of B, or the
Why is there a
opposite.
dash underneath?
Because it could be equal.
Could be equal also.
Yeah.
Okay, so subset or equal.
Oh. that's-
Proper subset or equal.
Yeah.
This one is
There's at least
subset, but
there's
not
at least one
equal.
thing in B that's not in
Right?
it.
Yeah, so
Yeah.
there is an element here that's not in this. Okay, clear?
Yep.
Yes, Usman?
Yeah.
Okay, all right, now, so maybe that helps you understand this better. So you've got lots of whatever, sets. Sets have these relationships, either this type of relationship or this type of relationship. And then you're asked to output the minimum and the maximum number of distinct sets, distinct classes.
Yeah.
What does that mean? So let's look at some examples. Yeah?
Yeah.
So here are some examples. Let's look at the first two. This one says that there are there's one relationship of the type subset or equals, and it says P is a subset of or equal to NP, and there are no relationships of the type subset but not equal to. So here we just don't know. There are only two sets here. One may be a subset of the other. So either they're equal or they're not. So the minimum you can have is if they're equal, maximum is if they're not. So the answer is 1 for equal, and 1 for minimum and 2 for maximum. Let me make sure everyone understood this, because there's no point in moving further if you didn't understand that. That's the easiest of the case. Everyone okay with that? Not quite? Go over it again?
Yeah. Mm-hmm.
So, one says how many relationships of the kind subset or equals. 0 means there are no relationships of the kind subset or not equals. Clear? So, therefore, this relationship is of the kind subset or equals. So P is one subset, so P is one set, NP is another set, and it says P is a subset or equal to NP. And now you're asked the question, output what? The minimum and the maximum number of distinct entities or distinct sets. Now, if P and NP, well, firstly, they could be equal, so therefore they're not distinct. If they're not distinct, there's only one distinct item because P and NP are the same, right? But it's also possible that one is a strict subset of the other, in which case there are two distinct entities, in which case the maximum is 2. Clear? Yeah. All right. Now let's look at this one here. This one says, again, there's only one relationship, but this time the relationship is of the kind, the second kind, namely it's subset but not strictly equal to. By the way, P and NP are the ones from complexity theory that stands for polynomial time and non-deterministic polynomial time. And it's well-known open question that we don't know whether they're equal or not.
$1 million.
$1 million, yeah. Well, $1 million is the least of the things that you get.
Yeah.
You'll be a very happy man. Not to worry about them. You'll be very famous. Elon Musk will be coming and talking to you. The second one says that this is a subset but not equal to all. Okay, these are just two sets, R and all. This one is a strict subset of this. It's not equal. It's not going to be equal. So therefore, there are two distinct subsets. Both of these are definitely different. And so therefore, the minimum number and the maximum number are both 2. Clear? Okay, these were the two easy examples. Now things get a little more interesting. Are you ready for this?
Mm-hmm.
Okay, this one says, you have 3 relationships. All 3 relationships are of the kind subset or equals. So this is a subset or equal to this. This is a subset or equal to this. And this is a subset or equal to this. Now let's draw a picture. Since I can stand here, I'm going to turn this into my board. All right. So if you go over there, it says QMIP. It says QMIP is a subset or equal to what? MIP star. That's over here, right? That's MIP star. And that in turn is a subset or equal to QMIP. No, sorry, we have RE. This is RE. Right? And then it says RE is a subset or equal to QMIP. What does this mean?
They're equal.
It means they're all equal. Okay, there's
Yeah.
nothing here that's not in this. There's nothing here that's not in this because they're all equal.
Yeah.
Clear? So therefore, the correct answer is there's only one distinct entity. Doesn't matter which one you call it, they're all the same. Clear? Ian, good?
Yeah.
Okay, Nick, the problem is here. You know which one? You can read that over there.
And I think I understood what you said with the
Okay,
this side.
with this example. All right. So now we're going to go to the 4th example, which is the only non-trivial one here.
They draw it out for you all the way at the top.
Nick has seen this problem?
No, I'm saying this test case is, they have a diagram at the top of the problem.
Right, I know. You can actually see that here. That's the picture. This is from real computer science. So, but it's a good idea for us to look at this here because that's how our input is going to be provided. We're not going to draw pictures like this. Instead, we're going to draw a picture like what you just saw, where each node is. By the way, if you could draw a picture like that and say QMIP is a subset or equivalent to MIP RE, MIP star, which in turn is a subset or equal to RE, and this in turn is a subset or equal to this. this is the picture you end up with if you were to draw a picture of what they do. In fact, they kind of tell you in this hint somewhere here that you may want to draw a picture like this where you use bold lines, solid lines for, oh, you want to use solid lines for not equal to, and the other one is dash, so we could do that. So, oh, that was too fast. Oh, sorry. Something's not going well here. Okay, so this is like that, like that. That's how the picture will end up with if you were to draw it the way they're suggesting here. They don't really give that in the text, but they do say so in the picture. That's fine. Okay, so let's go to this picture, this example here. It says that in this example, there are 11 relationships of the kind subset or equal to, and 8 relationships of the kind strict subset. So I think that's 3, 3, 6, 3, 9, and 2, 11. Everything until here is all subset or equal to. These are all strict subsets, right? What we're going to do is to draw a picture here and see if we can make sense out of this. So I'm going to erase this part so that we have enough space. We could use the picture that they had before and draw this. So let's start to draw here. It says NC is a subset or equal to P. P is a subset or equal to BPP. P is also a subset or equal to NP. And it's also a subset or equal to co-NP. Right? Then BPP is contained in BQP. Sorry. By the way, each of these dotted things is an open problem. If you want to solve one of these, feel free. BQP is contained in P space. And NP is also contained in P space, and co-NP is also contained in P space. All right. And then you have P space contained in exponential time. Non-deterministic exponential time, which in turn is contained in differential space. Okay, that's what you have with the subset or equal to conditions. Now you get all the remaining 8 strict containments. And the question is, how do we draw this? Well, it says that this is strictly contained in this is strictly contained in this is strictly, sorry, this guy is also contained in this, that guy is contained in P space. And so you see here that NC and P space show up again, and so does exponential space. So there are some things that are repeated, but there are many new things here, okay? So we're gonna try and use up the exponential NC and P space here and see if we can draw this more clearly. So we get regular expressions, that's REG, which is strictly contained in context-free languages. So this time it's going to be a solid line. So that's CFL. CFL is contained in NC, right? Then NC, CFL is also contained in CSL. And then it says NC is contained in P space and CSL is contained in P space. So this here is contained in P space. This here is contained in P space. But these are solid lines as opposed to the dotted lines. And then we have something that seems to be disconnected, but it's starting from exponential space there. It says exponential space is contained in R, which is contained strictly in RE, which is contained in all, right? Is it all? Yeah. So this is the hierarchy that you're given, okay? Now, question is, what do we do here? And you're asked to figure out the minimum and the maximum number of distinct entities in this case. So, in order to figure out the minimum one, we saw in the previous example, oh, yeah, don't really need this here, no? Okay, let's keep that on. In order to figure out the minimum, we focus on the solid lines or the dotted lines?
Dotted.
We want the dotted because the dotted could just merge, essentially, right? So it's possible that this merges with this, or this merges with this, or all of them together merge with each other. However, we have to make sure that the things that are connected by solid lines never merge with each other. So that means you have a whole bunch of things here. There's 1, 2, 3, 4, 5 guys. These 5 guys could all be with NC, could all be with P space, or they could be split, where some things are part of NC and other things are part of P space. This is all possible. And so essentially all of these will not figure in our minimum ones, because in the minimum case, essentially all these will disappear, right? Because all of these, and then you also have this one here. Now remember, this is so these will disappear, 1, 2, 3, 4, 5 will disappear. And then over here, this essentially could go all the way, it could take up all of these. All 3 of these could disappear and become part of P space. So these 3 will go, these 5 will go, the remainder is going to stay without any change. So that means you're going to end up with 1, 2, 3, 4, 5. 6, 7,
I see
8,
now.
something is, yes, so yeah, there is one other issue here that you have to kind of figure out. So one way to kind of think about these dotted lines is that because we are getting rid of these, so remember, these are things that are simply going to be thrown out because they could become part of anything you want. However, how did this become 7? So you still have 5 plus 4, 9. Sorry, this can all be together. So 5 plus 3, 8. How does this 8 become 7? What was that logic now?
Because
Right.
also PS space is inside NC. I'm just saying.
Oh, am I missing one?
No, I'm just saying,
Yeah.
from what I'm seeing, we also have the N that
This and
PS
this are
space,
distinct.
yeah.
Right. They are distinct, so that's why I counted 1, 2, 3. Oh, that's right. So,
Yeah.
so it's possible that these 2 can be merged. All we know is that this is distinct from this is distinct from this. Both of these are distinct from this, but these 2 could potentially be the same. And so therefore, anytime you get this branch thing that meets again, you can reduce, for each of those paths, you can reduce those guys. Now, if there are more than one things on that path, you have to do something else, but let's worry about that more later on. At least for this example, you get 1, 2, these two become 1, so that's 3. This is 4, and then 5, 6, and 7. Is that clear? So that's how you get a minimum of 7 distinct items in the minimum case. And what's the maximum? The maximum is that all these guys are
possible
distinct.
nodes,
Yeah, each of the subset or equal to is a not equal to, and in that case, and these guys for which you don't have any relationships could also be distinct, and so therefore you just throw them out. And so you get all of these, and here you'll see that's 4, 4, 4, 8, and 2, 10, 10 and 6 is 16, and that's how you get the 16. Okay? Now the question is, how do we do this computationally and how do we do this efficiently? We're told that m and n can be as big as what?
100,000?
10 to the 5?
I think so.
So that means the moment you see 10 to the 5, what is the first thing that should enter your mind? You should know that n times m or n squared or m squared is not going to work out for you. Okay? So those are the clues that should go immediately into your head, which means you need something that's roughly linear time. It's okay if there is a log n factor somewhere, but it just needs to be a linear time algorithm. All right, so now what do we do and how do we get this? Well, so the one way to approach this is to first of all remove, only focus on the solid lines, right? So if you only focus on the solid lines, essentially all these will get thrown out. All these will get thrown out. Remember, now you're trying to get the minimum number. So what we can do is to say we're going to throw away this. In fact, it's not the nodes that we're going to throw away, but we're just going to remove these. We're going to actually essentially just merge it with one end or the other. Okay, wherever we can, we just try and merge them. So now you're going to be left with essentially two connected components. One is going to have that part, and the other that's going to, oh, we can't throw away this, I'm sorry. Yeah, you have to keep that one, and so that's what we're going to be, we're going to end up with. Right.
Maybe what we count is the edges, the solid edges. In this case it will be 8, but since we're merging CSL and NC because they have the same source and...
Right, the question is how do we recognize this, and what, and that I can make this a little more complex by adding another node here on this path. Then what happens? So those are things that you have to worry about. So let's hold that first. First, let's figure out what we're going to do with the dashed lines and take care of those completely. Now, what if there are other possibilities as well. It's possible that there is a disconnected piece with just dashed lines. Then what do I do? Right? So, or there could be a disconnected piece with just solid lines. So those are all things that we have to take care of. We can't just ignore them. A bunch of smaller cases, but each of those are fairly clear. Here there's one other thing I haven't quite figured out. Do I get rid of this or not? Right. So the easiest thing to do is for each of the instead of what I said, namely removing these edges, removing these vertices, a better way to do this is to arbitrarily shrink all the dotted lines, except when something is so for instance, if I shrink this edge, then this becomes merged with that. Okay. And that way I can merge essentially all of these with NC, but I cannot merge this guy with that because this is reachable. P space is reachable from NC using a solid line. So I have to check on reachability in order to figure out what things I cannot merge. So that's one way to think about all of this. But then what happens here is that this one will get essentially merged with P space. And then you will simply have a solid line from here to R. And then all you're left with is to figure out what to do with things here. Now, there is one other little thing to kind of worry about, and then that happened in the other example that we looked at, namely, let me use a different color here. If you had a dashed line, sorry, a bunch of dashed edges, essentially what we're going to do is to merge them. So this one will shrink, and we'll contract this edge, and these two will become one vertex, right? Same thing here, this edge we will contract it so that they become one vertex. Now, what if I have a vertex going back here? This is a slightly special case because here there is no doubt about minimum and maximum. In this case, you have to report that this is just one vertex. In fact, that they're exactly the same, because you can't have this being a subset of this is a subset of this is a subset of this, and this being a subset of this. This is like that picture we drew, and when that happens, your minimum and maximum will be exactly the same. So this is one case that you have to worry about. So cycles in the dotted graph are things that you have to deal with separately. Those are things you actually have to shrink to one vertex. You don't have a choice.
Yeah.
You can't count it separately for the maximum. So that's one thing to worry about. So here there are no cycles in the dashed ones, and so therefore we'll arbitrarily shrink these edges, except that we can't shrink all the dotted edges, otherwise this and this will also get contracted and merged, and we can't allow that. So we can only merge things that are not reachable using dashed lines, using solid lines. Yeah? So therefore all these will disappear. What happens here is that all this will disappear, and you will directly get an edge from here to R. And then you can count the remainder for your minimum, except that now we have to worry about what happens with this part here. Now here, we have to check whether it's a tree or not. Whether it's a tree or a general DAG. What happens if there is a cycle in your solid lines?
Contradiction occurs.
That's where you will have a contradiction, because you're saying A is strictly a subset of B, B is strictly a subset of C, and C is strictly a subset of A. This is not going to happen. So you can't allow contradiction. So therefore, your solid lines will never have a cycle. You can say, I assume they say something about that.
Yeah, the last line says the relations between classes will not imply any logical contradictions.
Excellent. So that's simply for you to take care of that case. So no cycles in the solid lines. That means you're only left with two possibilities. Either it's a tree. So if I only focus on the solid lines, either it's a tree or it's a DAG. Now if it's a DAG, you have to worry about this a little bit more. So let's assume it's a tree. It's an easy case. If it's a tree, you just count them all as separate for minimum and maximum. And that's it, you're done then, right? Your minimum is going to be after shrinking all these other dotted edges, and the maximum is going to be if you kept them all distinct. Now, right. So now let's talk about what happens if you have a complex graph, but we're only focusing on the solid edges. we're only focusing on the solid edges, and there is it's not a tree, but it's a DAG. So let's draw a complicated one here, just so that we understand what's going on. This could look used to be. So what if I have a graph that looks like this, right? So this is an easy case. This is similar to what we had there. I could put more things here and then merge them. So in this case, I have 1, 2, 3, 4, 5, 6, 7. So if I have something like this, how many will I have in terms of minimum and maximum? That's what we have to kind of figure out. Now the maximum is easy. Maximum is if they're all distant. The minimum has a problem because these things meet back here, which means something here could be the same as something there. In fact, more than one thing here could be the same as more than one thing over there, without it being a contradiction. So it's possible, for instance, that 2 and 5 are really the same, yeah? Or it could be 2 and 4 or 2 and 6. So that would simply reduce the number for the minimum, right? It's also possible that not just 2 and 5, but also 3 and 6 simultaneously are the same. This also is possible. So we have to try and match things. Now, in this case, it would be easy because for the minimum, I only have to count 1, 2, and 3. Essentially, I have to match things on either path and reduce that number. Is that clear? So I would get 1, 2, 3, 4, and 5 for the minimum number, and 7 for the maximum number. Now, what if I have something a little more tricky? What if I throw in a third path, right? What if I, oops. Now what? What if I throw in, let's say, some extra edges? What if I throw in this edge? What if I throw in more edges? So I could start to make this more complicated. It's still a DAG. There are no cycles. There are no directed cycles, but it gets nasty. So in all these cases, you see that we could have a problem. Now, if there are only 2 paths, then all I have to do is to match things and make a maximum matching and then reduce the number by that many. If I have more, then, as I said, things get complicated. What if I make this a little bit simpler and I have this? Now what? So what is the minimum number and what's the maximum number? So you see that things are getting quite complex, right? Because it's possible that 2, 5, and 8 are the same, right? In the worst case. It's possible that 3, sorry, actually I should have done something a little different. Let me do 2, 4, and 8. I could have 3, 5, and 9 to be the same. And I could have 6 and 10 to be the same. Right? So.
Okay, so we have to check the depth, or how many steps away it is.
That's right. So it's some kind of a breadth first search process that's happening, and you're trying to cross out as many of these vertices as possible. So you're absolutely right. The way to approach this is as a breadth first search. which you do from here, and then at each level you try and cross out as many of these as possible. Yeah.
Oh, yeah.
And at each level you can combine as many as you want. They could all be the same and you can throw them out. Now, if there were other cross edges like the ones I showed you, then breadth first search would have figured out that the depth are different. And we can take care of that too. In case we want to take care of that, we can draw another picture here. So we could do something like this. If you have something like that, and if you throw in some more edges here, like that and like that, and I don't know, you can throw in as many edges as we want to confuse things. If you were to do depth first search, what will happen is that you'll get 1, then these all will be 2, and so since there are 2, I can combine them and throw them away, right? So I could take all these 2 and throw them away. And then I have 3. So that would be this, this, and that, and looks like I can throw those 3 away, right? And then I would have 4, which is these 2 guys, and I can throw that away, and then I think that's all I can throw away. Is that right? Yeah.
Does the destination matter?
Oh wait, this one too. Something is wrong. Something is wrong. So
What about now?
So this would be 3, right? Let me do this again. This would be 3. That would be 3. That would be 3. Now this would be 4. This would be 4. This would be 4. And this would be 4. And this would be, right?
Mhm.
Yeah.
Wait, I can't put this last 4. Because not all its parents are marked yet. So both of these would essentially be, this would be 5 and this would be 6, right? Because your depth first search would, breadth first search would have reached here already.
Mhm.
Wouldn't the very bottom one
So
also
I
be
think,
5?
sorry?
Wouldn't the very bottom one also be 5? Because its parent, or at least one of its like predecessors, is
This
at level
edge
4.
makes it not the same, you can't.
So we're not taking the minimum.
So that means we're not doing breadth first search, we're actually doing this thing called, what is that called? What is that numbering called? Where you try and linearize it. I'm blanking out. Topological sort. Remember this?
Oh.
So in
yeah.
topological sort, so if we do topological sort, it becomes much more clear. So for instance, I could do 1, and then this would be 2, this would be 3, this would be 4, right? Then I would have 5, 6, 7, right? Then I would have 8, 9, and I can't do 10 yet because I haven't quite labeled all the parents. And then I would have 10, and then I would have 11, right? And now you have to figure out what blocks of these I can combine and just label together. So this is actually probably the most reasonable thing to do. You take your DAG, do topological sort, and then figure out which of these don't have any edges, solid edges going from one set to another, and you can combine all of those and count your minimum. So now all you do is you write this down. You write down 1, 2, 3, 4, 5, 6 up to 11, and then figure out that 1 will be of course separate. Then you could have 2, 3, 4 because there are no solid edges connecting them, and then 5, 6, 7 will be together, and then 8 and 9 will be together, and then 10 will be separate, and 11 will be separate. So therefore, at the least, you'll have 1, 2, 3, 4, 5, 6 different entities for the minimum, and for the maximum, you'll just have 11.
Maybe I'm misunderstanding the problem a little bit.
Sorry?
What happens if you have two nodes that are in the same depth, but they're not going to the same destination? We can't say that they're the same at that point, right?
No, we're not saying they're the same, we're saying they could be the same.
Could be.
Remember, what we're trying to do is to minimize the number of things we're putting together. Now, it's true that 2 could have been the same as 5, but that's not going to change how many things you're eliminating at the same time. And so, in the end, the count will be the same. Is that correct?
Yeah, I don't really understand that much.
There is something that looks incorrect, so hold on a second. Can I erase this part here?
Yeah.
Let's see if there is a problem. This does not mean that there is a problem. What if you have let's say you have something like this, right? So what would happen with our idea of doing topological sort? This would get 1, 2, 3. I'd have 4, 5, 6. Doesn't matter how I label this. 7, 8, 9. And I'd have 10, 11. 12, 13, 14, and 15. I see a problem already. Would I have been better off combining 4 and 5 with these guys? See? What's the minimum and what's the maximum here? Maximum, of course, is 15, right? That's clear. So what's the minimum? One has to be separate. 15 has to be separate.
Well, 12, 13, and 14 can probably be merged.
12, 13, and 14 can be merged, but I could also merge it with some more things. So should I just do it separately?
No.
Or should I combine it with things on this side? But since I have fewer things here, this would get merged with something else, so I would probably do 2 and 3. I would do 4, 5, and 6. Then I would do just 7, 8, and 9, right? Then I would do 10, I will not do 11, then I will do 12, 13, 14. This would give me how many? 1, 2, 3, 4, 5, 6, 7, 8. So it gives me 8. Now, can I combine in a different way and get less than 8? Let's see. If I were to combine, if I don't combine any of these, if I only combine 2 with 11, right? Yeah, I could have numbered it so that I have 2, 3, 4, 5, and then 6, right? Then 7. Now what if I number them weirdly? Then what happens? So they don't have to be together, it seems.
But we get the same result.
Is it? Are
Yeah,
you
if
sure?
you combine, yeah.
What if I combine 7, 8, 5, 12, 13, and 14? You're saying I'll still get the same result? I'm gonna combine this. Okay? That's 1. And then, I don't know, I combine 4 with something.
11.
9, right?
9, okay.
Combine 2 with 6. Do I still get 8? 1, 2,
No.
3, 4,
Hold on.
5, 6, 7, 8. I still
Yeah,
get
same.
8. Okay, it's the longest path that determines it, so maybe it's okay. Yeah. Yeah, I think we can probably prove that this is correct because it's determined by the longest path from here to here.
Okay.
So that's why it's sort of okay.
Yeah.
Essentially, that's what determines it. 1, 2, 3, 4, 5, 6, 7, 8, and that's the number that you get.
Okay.
So if there are shorter paths, you can just throw it away because you combine them. But if you had extra edges in between, then things get very messy. So for instance, if I throw in an edge from 5 to 13, then things become way more messy. Yeah, not sure if some of the things we say are still, shall we try that? Okay, let's get rid of this blue stuff. And so let's say I throw in some edges. Let's say, what did I say, 5 to 13, maybe 8 to 14, right? If I did this, now what? We still have to look at the longest path.
Yeah.
Yeah, and yes, this path becomes long, but it's not the longest. And so you're still kind of okay. I could put in 2 to 6 and then 9 to 4. Now I'll get some nasty long paths like that, right? But are they still, is it still any longer? 1, 2, 3, 4, 5, 6, 7. So it's still only 7. So it just depends on the longest path, and I think we're okay with this. Essentially, it's saying that we're grouping things based on how far away they are from here, right? Or the longest path from here to wherever. And so we'll sort them out, we'll put them together and throw them out. And then this will only get the number, the distance from the longest path from the start. And since we can never have things going backwards like this, well, why not? Why can't we have that? Let's try that. What did I do? Okay. What if I did 8 to 3? well, then this guy won't get number 3, so I think we're okay. Sorry, yeah, just beginning to doubt myself. Is this making sense? So we use topological sort, and then we simply remove. Use topological sort and find the length of the longest path. But longest path is not a good idea, so what do we do? Topological numbering will do, topological sort will get you. The only concern I have is how do we group them?
Do you need to group them if you have the longest path?
Finding longest path is somewhat dangerous because, well, in a general directed graph, finding the longest path is an NPR problem. So there are no good algorithms for it. But in this case, it's a DAG. So what happens? Since we're doing topological sort, I think we're going to be okay. So essentially, we shouldn't be doing topological sort like this, but we should just number them differently. Let me try that again. So I number this as 1. I number both of these as 2 because their parents have been labeled as 1. And I'll label all of these as 3 because their parents have been labeled as 2. I'll label all of these as 4. And the good thing is that anything that's labeled as 4, there won't be edges connecting them, right? Right? If there was an edge from 8 to 3, from here to here, then this guy can't be numbered, this guy can't be numbered as 4, right? So all the parents must have been numbered before we number anything.
Okay.
That's what topological sort takes care of. So therefore, when we number them, they can be put together and labeled. So you're right. So then this becomes 5, this becomes 6, these become 7, and this becomes 1. So you're okay. So that'll give you your minimum number, and the maximum number, of course, is easy. Are we okay with this? By the way, what happens if you throw in some dotted edges here? What if there's a dotted edge from, I don't know, 3 to 8?
Were those the ones that we ignored because?
Sorry?
Were those the ones that we ignored because there was a different way to get there?
No,
A
we
different
didn't quite ignore
solid
it.
line?
I think
We couldn't
it
merge
comes
them.
to under 4, and so that's the longest part, the longest path. So it will be 1, 2, 3.
Well, remember, I can throw this dotted edge from
Exactly.
anywhere to anywhere to confuse us. My question is, does it mess up anything that we did? Or what do I do with those edges? Should I just throw it away?
I think that one we could end up ignoring, she's right, because if we did try to minimize the, considering
Yeah.
that edge and then put the, level 2, 1 through 3 down to level 4, then it would make the minimum 8. So if we just ignored it and followed the solid edges, or no, it would make the minimum 9. And so if we just follow the solid edges, it would still be 8.
Well, the question
so
is, can we?
should I take that into account and do the numbering as if those were real solid edges, or should I not look at those edges, or what should I do? Right? What if there was an edge, this one was kind of nicely behaving. What if I throw in an edge from Well, actually, yeah, let's do the same thing, but except that we'll reverse the direction of the edge. What now? Are you gonna be okay with whatever you did? Hmm. You could take a simpler example.
So this means
such
that,
as- Give me
this means,
just a second. You could take a simpler example like this. What do we do? Yes, you're saying?
so this means, I kinda lost it. This means that 8 and 3 cannot be taken as being on the same level because they can't be the same.
No, all it's saying is 8 could be
They could be
a
the same.
subset of 3 or equal to
Or
3. That's
equal
all
to
it
three,
says.
Yeah.
It doesn't give you any, there's no commitment.
I think that would only be true if it was strict.
Sorry?
Oh, I think the comment that Ian made about not being able to group 8 and 3 together would only be true if we took that edge as being strict.
Mhm.
Because if it's strict, then there's no way that we can group 8 and 3. So
True, yeah, then the longest path becomes much, much longer.
Yeah.
Right?
yeah,
So what should we do here?
I'm wondering if anything even changes.
It almost looks to me like you should make it a solid edge, right?
Yeah, I think we have to make it a solid edge. In the previous problem, when we had NC and PES space, we actually had the dotted line in some way, but we had to take it into account like as a solid one because we already have one.
Where, which one?
Between NC and PES space.
No, there we were told that that's a solid line, so it's not, yeah, sure, there was a dotted path. Or you're saying we also knew that NC was possibly a subset of P space. Well, for that matter, what if I threw in a dotted edge from here to here? That one is useless information.
Yeah.
Because we know that this is a strict subset of this is a strict subset of this, so why are you telling me that this could be a subset or equal to this? So we should be throwing away edges that are already reachable by solid paths. So those are things that should be strictly thrown out. They should not be part of any consideration. So that's one cleanup that we have to do. So in fact, this edge should simply be deleted. Whereas that edge from 8 to 3, there was no solid path that goes from 8 to 3.
So it has to be complete.
And so we have to do something else with it. So the question is what to do. Should we convert it into a solid edge, or should we throw it away, or what are we doing?
Well, if there's a chance that it could be going through that, then I think that we need to treat it as a solid edge for the minimum, because if not, then we're gonna have cases where, like, something got passed with a solid edge and we weren't counting.
Yeah, you're right. In fact,
Change the longest path here.
Yeah.
in fact, these two edges are contradictory. Now, you can't have this being a subset of that and that being a subset of this, can it?
Can you repeat that?
Could be.
Could you repeat that, Giri?
supposing both these edges existed, right? This black edge and,
From 2 to 13?
with 2 to 13, we already ruled it out, so let
Yeah,
me make
okay.
that a little bit different. Let me make that from two to 14, okay?
Okay.
So there's no, it's not doing any harm. But now we're saying 2 is a subset of 14. Well, okay, sure, that's possible. But we're also saying 8, which is a superset of 2, is a subset of 3, which is a subset of 14. And that also is not contradictory. Oh, well, it is. Hold on. So 2 is a subset of 4, which is a subset of 3, which is a subset of 14. And 2 is a subset of 14. I guess that there is no contradiction.
Where are you
Right.
where are you getting that 4 is a subset of 3?
This dotted line here. Sorry, it's not 4, it's
Oh,
8.
it's 8.
Yeah, sorry, yeah.
I'm not seeing any cycles.
Sorry?
I'm still not seeing any cycles. So
I'm
I
not seeing
think
any problem, yeah. I'm
so
not
I
seeing a
think we're
problem.
still fine.
Yeah, I think this is fine. No, but what it does for us is that it lengthens the longest path. That's what I'm concerned about. If we treat this as a solid edge. If we don't, it doesn't do anything. Now, that's why we have to answer the question, what to do with that dotted line. The implication of this dotted line is that we can't match this and this anymore. These two can never be the same.
Yeah.
And that's why this is kind of critical. So it should be treated as a solid edge. So any dotted edge that doesn't connect two things that are already connected by solid paths, we should turn them into solid edges. This is something new. This I have not thought about. I don't know, this kind of messes things up. That's crazy. Wow.
Does it have to be thought of like that, or can you just think of it as for when there's a dotted edge that would raise the minimum, then you have to include it?
Then you'd have to test each one of these, then your complexity will go way up. Because for each edge, you have to kind of worry about whether it increases the path. What if there's a collection of these edges that increases the path? So there are all sorts of crazy things that could happen, right? If this dotted line should be treated as a solid line, remember in our previous case, in fact that picture may be up here in this problem. Because remember we had a bunch of dotted lines here, right? Should we create a solid line from this? Because we squished them first and then applied all the other methods, right? So when do we squish and when do we not?
Well, it seems like we switch when there's like a continuous dotted line. Once you have a solid line, you
If you're
can't.
given a
switch.
graph and you have no idea what this picture looks like here, it's easy to see, but in a general graph, you have no way of knowing where it is, where this edge is. You're not told whether these edges are given to you in any particular order.
Well, The way I think of it is like you
There's a
kind
little
of
path between the source
traversing
and
through the
the
graph.
target, and it's a solid line, we can,
Well, are you saying that if there's an edge from here to here, then life becomes very different?
a dotted edge.
Solid.
What if I throw in a solid edge from CSL to all? In fact, I know that for sure. I know that CSL is strictly contained in all.
Well, in that
Would
case,
that
we
mess
wouldn't.
us up with R and RE?
That wouldn't-
Solid?
So I'm not saying, I'm saying take it one node at a time. For example, if I'm at NC, right, and I'm looking at the connections that NC has, if I see that NC has a dotted line with P, I know that I can merge them.
Well, let me remind you that the whole thing has to be done in linear time, so you can't be going through this node by node analysis. It's not possible. We have to come up with a strategy that we just then apply consistently. I thought this idea of this topological sort would, well, first after cleaning up all the dotted edges and shrinking them, and then applying the topological sort would take care of it. But we just come up with a case where it's kind of messing things up. That's all I'm saying.
For when you're going through in linear time, could you just check from one node to the next, like if the previous one had, like you had come over a dotted line? or
Yeah, I
something
thought that was
too
the
close?
shrinking.
Sorry?
I thought that was already like the shrinking that we were doing.
Okay, so what shrinking are you gonna do here?
Yeah, here you wouldn't be able to do that kind of shrinking.
That's what I'm saying. So your dotted lines are messing up here. Because that edge essentially prevents us from merging this node and this node ever, right? They can never be equal because of the way they're related. When I do- Yeah, I think our topological sort will have to deal with this. It can't number this as 2 anymore. It's not possible. Because this has a parent that's not been labeled at that point. And so your numbering needs to be different, and you'll find this longest path essentially. But then I'm still not clear whether this should come after this and this should become 5. Well, it makes sense that it should be 5 because, or at least it should be 4. Because this could be the same as that. I think that makes sense. So yeah. So let me refine what I tried to say earlier. Where is this? Okay, so we're here. When we started, so let's just throw in this edge, okay? Let's forget about the other things, yeah? Let's say this edge over here. I cannot number this as 2. When I number this, all its parents should be numbered. Or it should be numbered at the same time. So this is what I'm going to do. I'm going to call that as 1. I'm going to call that as 2. This cannot be 2 anymore. This cannot be 3, 4, 5. None of these numbers are going to make sense anymore. Right? 7 is wrong. 7 is wrong. So I'm going to do 2. I'm going to do 3. I'm going to do 4 here. And this can be 4 as well. So within the 4s, you can have dotted edges, no problem, but you can't number this before you do before you number this guy's parents, because this is a subset of this is a subset of this. believe this? Because this is a solid edge and this is a dotted edge, it's equivalent to having a solid edge from here to here. That's what I'm saying. This has to be a strict subset of that. There's no other alternative. So, so that's, which is the equivalent of what I just said. Now, in our previous case, in that case, what do we have to do there? So the good thing is that by adding this edge, I can now remove this edge, right? Because that's not serving any purpose for us. And I can work this. And what happens here? This says this is a subset of this. So therefore, isn't that equivalent to throwing in an edge from here to here, right? And throwing in an edge from NC to there, right? And removing this edge. So we have to do this small operation before we carry on. Yeah. Yeah. Does that make sense? So I'm saying you remove this edge, but before that you have to add a solid edge from here to here and from here to here. Then you remove that edge by adding another edge from here to here, here to here. Remove that edge by adding one from here to here, here to here. Once you've done this, you're in good shape, then everything is just solid. These guys will go away because I've added this edge already. It takes care of all these edges. Are you with me? Now whether I can do this in linear time or not is a different matter. But at least this algorithm looks right. What if I end up adding a square of lots of edges, too many edges? It may be easier to just modify topological sort to make sure you don't number this before this, that's all. Maybe that may be an easier fix than what I'm suggesting with the edges. Because I may end up adding too many edges, and that's not a good sign. So the simple algorithm is apply topological sort, except that you make sure that if there's a solid edge from somewhere, you have to be numbered after this. If there's a dotted edge from somewhere, you have to be numbered at the same time as that or afterwards, whichever works. And so therefore, if there's a dotted edge, you could number these two as the same, and that would be okay. And so you end up with 1, 2, 3, and this would also be 3, this would also be 3, this would also be 3 because they're all at the same time as this. And that would be 4, 5, and 6. Why is it 6? Shouldn't it be 7 and 1? Oh, I may have missed one. Is it 1, 2, 3, 4?
Oh yeah,
5,
that's
6,
one,
7,
that's
7,
one.
5, 6, 7. So, well, I call this a 0, it's actually 1. The path is of length 6, but the numbers are 7. I think this looks like a more reasonable algorithm, and I would be willing to bet some money that it works. Are you happy with this? Jian?
I'm not sure.
You're not sure, okay. So the dotted edges tell you that you can't number the other end before this one, because the numbering tells you the possible ordering of subsets. Okay. it tells you that this guy cannot be a subset of the other one. If you've numbered things as 2, the 3 can never be a subset of 2. And so on. So this 3 can never be a subset of that 4. Is it? We call this, yeah, because of this, yeah, of course. Look, all we care about is the longest path. And so we are giving an algorithm to find the longest path. What we're saying is the following. We're saying that if there is a path, and if one of these edges is a dotted edge, and then it continues again, then these 2 may be numbered the same, but you cannot number this before before something else here. That's really what we're saying. So numbering these 2 together is no problem, which is what we're allowing it to do. But we're making sure that this is not numbered before this or one of these other ones. That we cannot allow. Because this here is a subset of this. It may be equal, but it's not. So therefore, this is equivalent to having an edge here solid that way. That's really what we're saying. And therefore, numbering these 2 the same is okay, which is what we allow here. So we're doing topological sort with the extra condition that if there's a dotted edge, then we never number things before the head of that dotted edge like that.
How do we do that though?
Sorry?
How do we do that?
We're applying plain topological sort. And
Like, couldn't we run into a
so
situation?
remember, the way topological sort works is for every node, we figure out how many parents remain to be numbered, right? So we're gonna count, so we're deciding whether to number this guy or not. Remember, there are gonna be a bunch of solid edges, and there are gonna be a bunch of dotted edges. What we're saying is, all these have to be numbered before, they should have been numbered, but these guys, it's okay to number them right at the same time. That's all we're saying. Right? Which means all these guys should have their parents to have been numbered prior, numbered 1 less at least. That's all we're doing. And so topological sort can take care of this. It will require some extra tests, but it seems doable to me. So this is the picture to have in mind. Let's stop here. I need to get ready for the next.